In this video, we're going to do some more practice with integration by substitution. First, let's review the steps for substitution that we went over in the last video. Step 1, we're going to replace u with the inside function. That is, we need to determine what is the inside function and the outside function. And we want to make sure that the derivative of the inside function is elsewhere in the problem. Step 2, we need to replace dx in the integral. So we're going to take the derivative of u, that is du dx, and do some algebra to solve for dx. Step 3, we need to rewrite everything in terms of x in terms of u, noting that we're going to be canceling the derivative of the inside out and all the x's should cancel. Note that if we have u and x both in the integral at this point, there's a mistake. If we're doing a definite integral, we need to rewrite the bounds as well in terms of u. Step 4, we're going to do our straightforward antiderivative. This is the payoff to all of our hard work. This is an easy step. We have made the integral easier to do. Step 5, put our answer back in terms of x, or we're going to evaluate the definite integral in terms of u. So we're going to look at 4 practice problems here. First one is the integral of 3/2 x to the 7th times 2 to the 3x to the 8th. We're getting some extra constants in these problems that are going to be harder to deal with, but again, the purpose is to now determine what is the inside and what is the outside function. And in this case, we do have some function composition, one being that we have 3x to the 8th all inside of 2 to the something. We're going to write that as 2 to the x. So that is the 2 to the 3x to the 8th. And how we know that that's the correct choice for the in function is because the derivative of 3x to the 8th has an x to the 7th term, and that's the extra term in our integrand. So step 1 here is now an easy step since we identified the inside function. We're going to let u equal 3x to the 8th. Step 2, we're going to take the derivative of u with respect to x, and that's going to give us 8 times 3 is 24 x to the 7th. And that x to the 7th is key. We know that we have an x to the 7th elsewhere in the integrand, and that's something that we need to have in these problems. Step 2, we also need to solve for dx. So we're going to multiply both sides by dx, get a 24x to the 7th dx, and we're going to divide by the derivative of the inside, the 24x to the 7th. Step 3, we're going to replace everything in the integral. So we're going to take all of this nonsense and we're going to replace it in the integral. So we have a 3/2 x to the 7th that we're not going to touch yet. We have a 2 to the u power times dx is going to be du over 24x to the 7th. And we know we've done everything correct if we can cancel out all of the x's, which we can. The next little step here is we got to make sure that our constants are all out in front. Right here we have a 3/2 and a 1/24, 1 over 24, 2 to the u du. And we can write that as a constant, 1 over 16, 2 to the u du. So step 4 here is actually take the antiderivative. Let's remember that the derivative of 2 to the x is 2 to the x natural log of 2. So that means that the antiderivative of 2 to the x is going to be 1 over natural log of 2 times 2 to the x in order to make sure that constant cancels out. plus a constant c. So step 4, we just kind of already did that. That's going to be 1/16 times 1 over natural log of 2 times 2 to the u plus c. And step 5, we want to rewrite everything in terms of x. So we have 1 over 16 natural log of 2 times 2 to the 3x to the 8th plus c. And there is our answer. This will actually end up being one of the more complicated antiderivatives that we have to do in this section with that 2 to the u, but I wanted to show some more complicated ones in this video. Next problem, we have a definite integral from -1 to 3 of the square root of 2t plus 3. Now this problem is a little bit tricky because there doesn't seem to be anything else multiplied by this function composition, but we'll see why this is an okay thing. So first, let's identify the inside and outside function. Here, the only kind of function composition we have is 2t plus 3 is inside of square root of something, or square root of x. Now, in order for this to work, the derivative of 2t plus 3 has to be somewhere else in the problem, but that derivative is just 2, and that's just a constant, so it's not going to make much of a difference. And this is kind of an easy example of substitution. In fact, the only reason it might be difficult is because it doesn't have some of the same complexities that we may be used to. So let's go through the step-by-step process again. Step 1, we're going to rewrite u as our inside function. Note that we should have a square root of t, since we're dealing with t here. Step 2, we're going to find the derivative of u, not with respect to x, but with respect to our variable t. In this case, that is just 2. And if we solve for dt, we're going to multiply by dt, divide by 2, and step 3, we're going to rewrite everything in the integral. So we're going to take all this nonsense, we're going to bring it in here to get square root of u du over 2, but we also have to deal with the bounds because these bounds are in terms of t, and we need to change the bounds. In terms of u. So to do that, we're going to use our formula that u is equal to 2t plus 3. And for each bound, we have t equals -1 and t equals 3. We're going to plug it into that formula and get that u is equal to 2 times -1 plus 3 is 1, and u is equal to 2 times 3 plus 3, 9. So the bounds on our integral are these new values, 1 and 9, not the -1 and 3, because we need those to be u values. That's the extra thing that we have to do with definite integrals. Now we have step 4. Step 4 is we just need to take this easy antiderivative, which is a straightforward antiderivative. Let's write it as u to the 1/2 power. Note that we have a 1/2 out in front. That's from this 2 in the denominator. We're going to bring it out in front to get us the 1/2 here. And this antiderivative should be the 1/2 comes along for the ride. We're going to increase the power by 1 and divide by that new power. And we're going to evaluate from 1 to 9. So step 5 is actually do the evaluation. Note that 1/2 times 1/3 is going to be the same as 1/3. And we're going to have a 9 to the 3/2 minus 1 to the 3/2. And that's the same thing as square root of 9 cubed and square root of 1 cubed, which we can rewrite as 3 cubed and 1 cubed. And this will give us a big 9 minus 1/3, or 26/3, if we wanted to simplify that problem. Let's see another example here. Find the integral of natural log of x over x. This may not look like a substitution problem, or maybe it's a little bit tricky to see what is the inside and outside function. And what's really tricky here is that we have that the inside function is natural log. The reason that works is because the derivative of natural log is 1 over x, and that's somewhere else in the problem. Maybe it's better to write this as natural log of x times 1 over x dx. Now, what's really tricky about this problem is its simplicity, that the outside function is just x. There's no other complicated function. It's not x squared, it's just x to the first power. And that's an easy function to deal with. In fact, it's going to make our antiderivative very easy at the end. But it's just natural log inside of that. Let's see how this works. Step 1, we're going to rewrite u is equal to our inside function. Step 2, we're going to take the derivative of u with respect to x, and we're going to solve for dx. That's going to be du is going to be equal to dx over x. We can think about dividing by 1 over x, or we can just think about here as multiplying by x on both sides. This will give us x du is equal to dx. In step 3, we're going to take all of this and plug it into our integral. We will have u over x times x du, and although it's kind of flipped, the numerator and denominator, those x's still cancel out, and we are left with a u du, which is a very simple integral to do. So step 4, we have that this integral is going to be equal to 1/2 u squared plus c using the reverse power rule. Step 5, we're going to put it back in terms of x. So 1/2 natural log of x squared plus c. Again, we can see at the very beginning this outside function is kind of weird because it's simple, but at this point, we knew that we should have to take the antiderivative of just that simple function, just x or just u in this case. One more example here. Evaluate the integral from pi over 4 to pi over 2 of cosine over sine d theta. So the inside and outside function here, the inside function is going to be sine of theta. And the reason I know that is because the derivative of sine of theta is cosine, and that's somewhere else in the problem. The tricky part is that sine is inside of 1 over something, or 1 over theta in this case. So step 1 to find this derivative, antiderivative, is we let u equal the inside function sine theta. Step 2 is we're going to find the derivative of u with respect to theta. That is going to be our cosine of theta. And we are going to solve for d theta to replace it with our du. So we're going to multiply both sides by d theta, and then we are going to divide by our cosine of theta on both sides to give us d theta equals du over cosine of theta, which gets us to step 3, where we are going to translate our integral in terms of u. So right now we have our bounds are in terms of theta. We still need to change those, but we have a cosine of theta on the top. Sine of theta is u, and we have du over cosine of theta on the bottom. We can cancel out those cosine of thetas, and we're going to have to change the bounds in terms of u. So again, the way that we do that is we're going to use the formula that u is equal to sine of theta. So our first bound is that theta is equal to pi over 4. So that means that u is going to be equal to sine of pi over 4, which is going to be square root of 2 over 2. Second bound, theta equals pi over 2. So that means that we're going to have u is equal to sine of pi over 2, which is going to be equal to 1. So that means that our bounds in terms of u are going to be from square root of 2 over 2 to 1. And now we can go to step 4, which is actually take the antiderivative. So we have that this antiderivative, all in terms of u, is going to be equal to natural log of the absolute value of u evaluated from u equal to square root of 2 over 2 to 1. And since those are u values, we do not need to translate them back into theta values. We can just plug in at this moment. Let's call that step 5. And we have this is going to be equal to natural log of the absolute value of 1 minus the natural log of the absolute value of square root of 2 over 2. Natural log of 1 is 0, so we could say this whole thing is equal to negative natural log of square root of 2 over 2. When we're thinking about substitution problems, this seems like a very complicated process, especially with some stuff about the du, d theta, and replacing things. The more practice you get with these problems, the easier it gets, and sooner rather than later, substitution problems are going to become second nature. Please put in the practice until it starts to become more and more comfortable.